Sure.
So here I was doing the question one, and I think I got, I was wondering how to calculate the p-value given that I got this as my chi-square
Okay.
value.
So there is a chi-square table on the back of your book.
No, there's
So
not.
no? Okay.
I looked it up online, but
Yeah. So it's
yeah.
similar to a z-score test and a t-test. So basically you have your test statistics, which is your I think it's under your sum column. It's your test statistics, and then you're gonna compare that test statistics to your critical value. I'm not sure if that is the one because I didn't calculate it. But basically, first you have your chi-square, your calculated chi-square, like the notation chi is that kind of like the capital X. Um, and then you compare that value with the chi critical value, which you will find in a table. What you need in the table is just degrees of freedom and your alpha. So you have two parameters, your degrees of freedom and your alpha, and then you can find the chi critical value.
I don't think they gave the alpha in this one, so I just used 0.05 like usual.
Yeah. So basically, if like in the problem, it doesn't say what alpha to use, you just use 0.5. Sorry, it's 5%, 0.05.
So do you see this table?
No, I didn't. Can you just stop sharing and then share again, and maybe that helps?
Do you see it now?
Hi, Olivia. Okay, good to see you again.
Good to see you.
So Victor, do you see the table now?
Yeah.
Okay. So the critical value for 4 degrees of freedom at alpha would be 9.488 then. No.
Is that one tail or two tail?
I think yes.
I mean, these ones are always one tail.
For a chi-square test, it's always one tail because the distribution is non-symmetric, and it has a heavier tail on the right side, and it's not symmetric, and so it's always a one-tailed test.
So how do you know it's a chi-square in this case?
Because I think in the problem it asks you to use a chi-square, and basically a chi-square is a test for to test independence. So basically here there's there's two hypotheses. First, like each day is independent, and what that means is I guess it's a phone call. The phone call during each day are expected to be the same. So that means each day is being independent. And there could be another hypothesis, which is like each day is not independent. For example, I may have more calls during the Monday because that's the first day of a week, and a lot of people like they cannot call you in the weekend. They tend to call you during the Mondays. So maybe that's another hypothesis. So basically, when you try to understand if two or more data are independent or not, then you use a chi-square test.
Okay, got it. That makes sense.
So to calculate the chi-square, I got expected number of calls would be 200 because that's the number of calls divided by the number of days.
Yes.
And then this was the calculation I performed. You insert the day squared divided by 200 for each day.
Yes.
Add them all together. That's our test statistic. So now that I have the test statistic and the critical value from the table, do we subtract the two?
No, like it's similar to a z-score test or t-test. As long as your calculated value is less than your test statistic, is less than critical value, then you fail to reject the null hypothesis.
Yeah, but it says calculate the p-value for testing the null hypothesis. So I don't understand how the p-value comes about.
Okay, so what you're gonna do is maybe instead of putting in degrees of freedom and alpha in that chi-square table, in this case you're gonna put in 2.75 and the degrees of freedom, and then you locate what is the probability.
Right? So if I want,
like every time there's 3 parameters, as long as you have 2, you can get the third one from the table.
So it's about right here.
2.75, not 0.295.
Yeah, your like your calculated value is like 2 point something, right? So you gotta locate that 2 point something. But also the degrees of freedom should be 4.
So it's between 90% and 10%.
Yes. Yeah, it's not very precise in this table.
Maybe I can find another one.
Yeah, I think maybe.
Okay, and this one does the same thing.
I guess the point is it's like irrelevant.
Interesting.
But
like,
I mean,
does it like not really matter, right? Because normally your alpha would be 0.05.
Right.
So it could be anything greater than 10 or less than 90, regardless. It's
so
rejected.
Basically, the p-value in this question would be greater than 5%, because that's why you fail to reject the null hypothesis. But here, like I think the interval is like too broad. It's like between 10% and 90%. That is like too broad.
Yeah.
I don't know.
That's okay. So
I would say first you should absolutely write this. You should absolutely write down all of this kind of analysis. But if you can get a more precise p-value, that would be better. But I'm not sure how to find that.
Okay, so for here we're just gonna say it's is greater than 0.05 and less than 0.9 for right now.
It's greater than 0.1.
0.1.
It's on the table,
Yeah.
I think.
Yeah. Okay. Yeah. Okay. Yeah. Okay, and then. So do you think the staffing needs adjustment? But since we failed to reject it, they don't need any adjustment.
Yeah. So actually,
to fail would be greater than 9.488, right? At 5%.
Yes. So basically, we failed to reject the null hypothesis, meaning like we accept all those they are independent and they have the same expected cause, and we don't need to do any adjustments.
Oh, Paloma, do you want to explain this?
Which part?
This part, the part you shared.
Oh, I found a video that I just sent James that was also really good at explaining the chi-squared formula. Just in case. Do you mind if I move to question 2, or are you still working?
I think I'm all set with question 1. I'll try to figure out if I can find a more accurate chi-square on my own, but that's just gonna be Googling.
Yeah, I'm Googling and actually I find one. I can share the link in.
Our textbook does T, Z, but there's no P.
I think like looking at the data, it seems to be correct. Just wait a second.
I'm trying to see if there's one in the book. I don't think there is.
I don't think there is either.
Can you see the link here?
Yes.
Yeah, I think that calculator would be good.
Okay, so we got 2 points. 2.75 and 4 degrees of freedom at 5% alpha. They give us a p-value of 0.6. I'm gonna mute myself.
Yeah, I think it's good. I think it's good because that lies like between 0.1 and 0.9. I guess that's what you just find in that table, but it's not precise. I guess the answer of like in that calculator would be correct.
Okay, thank you. Plumman, you want to move on to 2?
Yeah. So really I just had it's pretty straightforward. But I had a question on if you divide all 3 of the age groups. So essentially, they're asking, this is like 2A, to compare, do you think the incidence of breathlessness among the coal miners depend on age? So based on the example in the slides, I kind of just did exactly what we did there. So ages 29, yes, they do have breathlessness. No, they don't have breathlessness. Divided that. Same thing with all the other age groups. And then once you get that value, do you divide all 3? How, my question is where do you go after you find the values comparing 29 to 30 to 49, or 30 to 49 to 50 plus, or 29 to 50 plus? How do you compare all 3? Because in the example in the PowerPoint, there's only two groups to compare.
Okay, so you are asking about the relative risk?
Yeah, how do we calculate the proportions from these numbers? Yeah. With go ahead.
Sorry, no, I was saying it's A. For A, I did odds ratio instead of relative risk, but maybe I should have done it the other way.
Okay, so first, what's your null hypothesis?
Can you post the question, James? Do you have a question?
Yeah.
I guess the null is that breathlessness causes, that breathlessness is dependent on age.
Okay, so if they are not, if they're independent on age, So what's your expected value of breathlessness? Like among all those columns, you could calculate an expected value. It's just like question one, but question one is more easy because you just use the total number divided by 5. But here it's like kind of trickier. But you will like you have so first on the first column, under 29 years old, have breathlessness, right? So if you assume independence of all those ages, the probability of I am under 29 and I have breathlessness is just equals to the probability of I'm under 92 multiplied by the probability of I have breathlessness, right? Because independence, the probability of A intersection B is just the probability of A multiplied by the probability of B. So kind of you have your expected number.
Okay.
Wait, can you explain that again? Sorry.
Okay, so wait a second. Can you stop sharing and maybe I can write on the.
Mhm.
Sure, thank you. So basically, so this is a like formula you learned during the first few weeks. So if independence holds, then the probability of A intersection B is just probability of A times the probability of B, right? And in this problem, basically, what is A and what is B? A is under 29 years old. This is A. And B, I have this problem. I have this breathlessness. This is B. So basically our null hypothesis is there's all those numbers are independent, right? The illness has nothing to do with the age, which from my intuition was wrong. So I'm trying to reject this null hypothesis. But assuming independent, this number should not be 48 because this 48 is our observed number. But what is our theoretical number if we assume independence? We're going to use this formula to calculate that. So basically, in the probability of the first column is A intersection B. It's here, A intersection B. To calculate that, we should find out what is PA and what is PB. So basically, the probability of I'm under 29 years old is just 3,743 divided by the total number of people. So this is PA. So we're kind of separating this like very complicated probability to two simple probability. So by looking at this table, because those like in this column, it shows the total number of people. Among them, 3,743 are under 29 years old. So the probability of one random person under 29 years old was simply 3,743 divided by the total number of people. This is our probability of A, probability of under 29. And assuming independence, right? Again, we find what is the probability of having breathlessness. So instead of looking at the column, we're now looking at rows. So, and again, the probability.
So you're essentially just weighting everything, right?
Yes, that's correct. So the probability of breathlessness is simply 2,221 divided by the total number of people. right? Because there's only two results. I have breathlessness or I don't have breathlessness. Among them, 2,221 people have breathlessness. So if a randomly selected people, you ask him what is the probability of having this problem, just use the 2,221 divided by the total number of people.
So would the expected value in yes and expected value in no be the same?
Now, it's not the same. I think it's not the same because so for example here, so now we're dealing with the first number, the 48. If we're dealing with this number, the probability of A and probability of B, actually they would change in this. So basic here, what is A? A is still my age is under 29 years old, but B becomes I don't have breathlessness, right? So in this case, PA. So in the second column, when we calculate this number, PA won't change, but PB will change. PB here instead we use this number divided by the total number of people. This is actually our probability of not having breathlessness. So for every number in this chart, by the way, this is sometimes called a contingent table, I think, contingent table. So in this contingent table, these are all their observed number, 48, 3,000, 3,695, all those numbers are observed number by experiment. But what I'm doing is I assume like this problem is independent of ages. What is my theoretical number? And I compare my theoretical number with the actual observed number. If there is a huge difference, then I reject my null hypothesis. I said, okay, they are not independent at all because the actual experiment shows the statistics are very different from my hypothesis, from my theoretical number, if I assume independence.
So I don't understand why for column A we did the total people in age 29 over the complete total. And then for the no column, we're not using the same total for ages 29.
We're using the same total. So basically for the no number,
Yeah.
this PA, the probability of having an age under 29 is unchanged, right? That makes sense. But the probability here the B changes. At the first column, the B is the event B is I have breathlessness. I have this problem. But in this one, when I calculate the theoretical number of this, my event B becomes I don't have breathlessness. Yeah, there is no, I don't have breathlessness. So basically, instead of using 2,221, because here means how many people have breathlessness, right? The probability of not having breathlessness, we use this number. We use 16,061. We use that number divided by the total number. So here the total number is in all cases the total number is unchanged, but
Okay.
maybe the numerator will change.
So that's going to give you your probability of breathlessness, yes, 29, 30 through 49, and 50 plus. And so then answering question A is just looking at those probabilities. Would you say that breathlessness depends on the age? Yes or no?
So after we calculate the probability, and as I said, we should have a theoretical expected number. But we use probability of A times probability of B. For example, for the first number, for the 48, its probability is the probability of I'm under 29 years old times the probability of I have breathlessness. This is the probability. But to get the expected value, every time we use the probability times the total number, we get the expected value, right? The probability of tossing a coin, of getting ahead, tossing a coin and getting ahead is 50%, and I toss the coin 10 times. What is my expected value of getting ahead? We just use 10 times 50%. So every time I use my probability times the total number of trials. So this is a first number. It's a contingent table. I would say it's contingent 1, 1. The expected value of this, the expected value of contingent table, first row, first column equals its probability times the total number of people, which is 18,282, I think. So this is my theoretical number, and that number, by the way, I think will be very different from 48, and it should be a lot larger than 48 if you think about it. Because I think if I like, my hypothesis is if I'm younger, then I'm less likely to have breathlessness. So the observed data, which is in real life, there's only 48 people under 29 years old getting breathlessness. But theoretically, if we assume they are independent, then no matter I'm under 29, no matter I'm over 50 years old, I should have pretty much a similar chance of getting breathlessness, and thus my theoretical number would be getting bigger. So what you're gonna do is, this is the theoretical number of the first row, first column. You should calculate the theoretical number of all 6 statistics, right? We have 648, 3695. We have here. So basically, you have 6 numbers, and actually that is your degrees of freedom. So the degrees of freedom is rho times 1, or rho minus 1. This is degrees of freedom in a chi-square test. I don't know if that's covered in the class. So the degrees of freedom is rho minus 1 times columns minus 1.
I can't see your screen. Are you writing something?
Oh, I'm sorry. Let me stop sharing and share it again.
So that would be 4 here. 4 degrees of freedom, because there's 6 rows.
Oh, I think in this case the degrees of freedom is just 2 minus 1 times 3 minus 1. So
James, can you see the bottom of Victor's screen? I can't.
Yeah, I can.
Oh, then it's just me.
So basically, what the
You wrote it
degrees
in
of,
like the corner.
okay, so basically why we use degrees of freedom is, like, I gave you the total number, right? I gave you 3,743. Then this 48 is actually is free. I call it it's free. But then 3,695, this number is not free. Actually, this number has to equal the total number divided by the first number. It's not free. And like, if we look at the vertical line here, I have the total number of yes. The total number is 2,221. And I would say the 48 and 612, these two numbers are free. I can give them whatever arbitrary number. But then the third one, 1561. It is not free. It has to be the total number 2221 divided by the first two numbers. So actually, in the contingent table, the degrees of freedom is calculated as row minus one. Minus one basically is this one, 1561, times columns minus one, basically is the 3695, because they are not free. As long as we settled all other numbers, these numbers are not free because we have to use the total number divided by the number that we settled. So in this case, we have three rows and two columns. So R equals 3 and C equals 2. Our degrees of freedom is only 2 in this case. And every time we have a null hypothesis, and then we have the test statistics, right? We just finished one very critical step of finding the test statistics, which is finding the expected value, assuming independence, which is PA times PB times N. So, and then we're gonna do like a chi-square test, right? I said this number, the column 1, row 1, this number would probably very different from 48, right? But what is our test statistics? It's a chi-square test. It's a chi-square, and I think James maybe know that formula because that's it. That's also used in the first question. Basically, that's your expected number subtract the observed number squared divided by the theoretical number. So basically, it's a C11. This is our calculated theoretical number under the assumption of independent, minus the actual observed number, which is 48, and I squared it. Divided by theoretical number is our calculated contingent table C11. So this is like the first number, the chi-square of the first data, and we have 6 data, so we should add on. We should do this 6 times. So basically, we should do it to measure what's the difference from our expected number and 48, and then we're gonna measure again what is the difference of our expected the second column, the first row second column. What's the difference between the expected value and its observed value, 3695. Again, we use our calculated expected value minus 3695 squared, and then divided by our expected value. And when we add on, and there's 6 parameters in this equation, and we sum them up, that is our final chi-square, calculated chi-square. That would be the test statistics of this problem.
Victor, if I could bring it back to these calculations, can I share my screen? Because I don't think I'm getting it exactly correct. Do you see my Excel?
Yes.
Okay. So I was trying to do this probability here, like you said. And so I took the total number of 29s and divided by the total number of people. Right, so I got these, but for the nose, like I don't understand why. Like it's just I did the same equation here, but then you were talking about PB and how it's these totals.
Basically, the probability there is the two probability multiplied together. You use the column like E5 divided by the total number. That is only the probability of M under 29 years old, right? But what you should put in that probability, in that like you said, like you calculated 0.204. Yeah, in this unit, what you're gonna put is the probability of you are under 29 years old, plus you are also have the problem of breathlessness.
So is it this number times this number?
Yes.
So over here, if I went like this times this calculation, oh, that's 0. Okay. There we go. And then did the same thing. And then here, it's the same calculation, but instead we're multiplying it by the nose.
What's your yes and no's? I'm not.
I'm sorry?
Like, how do you calculate your yes and the no?
Over here?
No, on the right. Yeah. There's two.
I took the total from yes divided by the total people.
Okay. Yeah. I think that's correct calculation.
You think?
Yeah. I think.
And then for no, I did the same thing, but with the nose.
Yeah.
So then these should. No, they don't add up to 1. Do these add up? So do all these add up to 1? Okay, that makes sense then. And so to get the expected now, if we do another,
You use your probability.
29, 30, 50. Yeah, now we have the probability for each probability. One. So it would be, so, shit. This times here.
No, you use your probability times the total number of people. Right, because we're calculating the probabilities. I just select a random person, and he has like 2.4% probability that that guy is both under 29 years old and have the problem of breathlessness. Now I have, instead of selecting one guy, I have 18,282 guys. So what is my expected value of under 29 plus have the problem of breathlessness? You use that probability multiplied by the total number of people.
And this would be the same equation with the total times probability. Hold on. No, that one's fine. So these are now our expected values, which we can use the chi-squared formula.
Yes, and by the way, you can add up all the rows and columns, and you find it's like magic that equals to the like your former table, because that's your expected value, and it's just under the hypothesis of independence. It doesn't change our like total number of people.
Okay, perfect. Like magic. And then these totals, I assume, would equal these totals as well.
Yeah, but like each rows and each columns, it's not different. It's the same. It should be the same.
Okay. Oh, it is.
And then you should do like what you have already done in the first question. You
Mhm.
use that long formula to calculate your test statistics, which is in this case the chi-square statistics. And that I think that number would be very, very huge, and you don't even have to look at the table to reject the null hypothesis.
Okay, so it'll be. Wait, let me go back here. So if I call this table 1 and this table 4, it would be table 1 cell minus table 4 cell all squared divided by table 4 cell. Does that make sense?
Yeah.
So it'd be like this number minus this number over this number.
Yeah.
That's what we did. That's what we did in question 1.
Yes.
And we do that for all 6.
You sum them up. Yes.
And sum them up, and we'll get, like we did here, the test statistic.
Yeah.
Okay. Actually, I could probably do that right now. Okay, that looks right. Okay, and then we're gonna auto sum. So that's our test statistic,
Yes.
or our chi-square,
Yeah.
if the calculations are correct.
Yeah. And you're gonna compare this value with the chi-critical value, which you can find on the table using degrees of freedom equals 2 and your selected alpha. Actually, like here your chi-square are so huge. You can first like open the table. I think you will find like
There it is.
yeah.
It's basically 0.
Yeah, and it makes sense, right? So
Mhm.
if I am younger, I am very less likely to have like breathlessness problems than those people who are older, especially those who are over 50 years old. And of course, the independence doesn't hold in this circumstance.
Okay, so yeah, it obviously, so we're rejecting the null hypothesis, which was it does not depend on age.
Oh, no, our null hypothesis is that The null hypothesis is they are not dependent on age.
That all these are independent.
Yes.
And so because this is so high, we can reject it,
Yes.
obviously. And then how, so this relative risk question, is that just comparing these probabilities here?
Oh, so basically, there is there's many ways to compare it, I think. Um, what a relatively risk of coal miners is. So basically, the relative risk is like for those who are. Oh, so first I think there's a typo. It's 50 plus, because
Yeah. Okay.
there's no 55 in the table. So
Oh,
basically,
go ahead.
we can see that uh, if I'm over 50 years old, then I have a higher risk of getting breathlessness than those people who are 30 to 49 or under 29. And the way you look at it is through that maybe the probability table you just created, but you should analyze those table a little bit. Or you can use you can like compare table 1 and maybe table 4. Um, and the difference actually, yeah, one way is you look at the difference between table 1 and table 4, right? The difference between your observed value and the hypothesis and the expected value, right? So for example, yeah, in the first data, the 29 years, that data, our expected value are much higher than the observed value. That means under the hypothesis of independence, I expect 454 people, which is under 29 years old, have the problem of breathlessness. That is assuming independence. However, in reality, in real world, when I do research, I find out there's only 48 people who is under 29 years old have the problem of breathlessness. Then I would say there's a low risk uh, of people under 29 years old getting the problem of breathlessness. Right? I can do some analysis using these two tables, and especially by looking at the difference. But here, I think um, the most easiest way to answer this question is you find out what is the absolute risk, and then you find out what is the relative risk. And basically the risk in this case, this term risk is basically another name for probability. Right? What is our relative probability of having that problem, right, compared with those younger people and older people? So, so if we go back to the homework problem, go back to that PDF sheet. Um, the absolute risk, also called absolute probability of a person under 29 years old getting the problem of breathlessness, is simply 48 divided by 3,743. You're just looking at the first row, use the yes divided by the total number. That is my risk of, if I'm a coal miner, this is my risk of getting the breathlessness, right? And then by the same token, we look at the second line and the third line, and I can find my absolute risk of getting the breathlessness problem. Okay, so this is your absolute risk. What is your relative risk? You just use the your absolute risk and do some algebraic calculation. So basically, from this chart, from the absolute risk chart, you can see like over 50 years old, that risk is 0.31, which is very high. So basically, that means if you are a coal miner and you are over 50 years old, then there is a 30% chance that you have breathlessness, right? That is actually very high probability. But if you're under 29 years old, that chance like reduced from 30% to a 1.2%, which is actually very low. So what is the relative risk compared with aged 29 years old and compared with 32 to 49 years old? You just use the absolute risk divided, you divide your absolute risk in two categories. In this case, it's like 31% divided by 6%, 6.39%. That is your relative risk compared with the middle-aged group. And if you use 21% divided by 1.2%, that is your relative risk compared with a young aged group. Yeah, maybe you can use this percentage score, but I mean it doesn't matter.
Well, I can change it back. I'm just confused. Are you saying we should divide these two numbers?
Because you already have the absolute risk of the
Yeah.
young aged group, of the middle aged group with the elder group, right? So
Yeah, this
now
is
you want to compare the risk between the older group and the middle aged group, right? So you just
Oh,
say,
okay.
oh, if I'm older, I'm like 5 times more risky to get that problem than the middle aged group. How you get that 5 times more risky? You just use 0.31 divided by 0.06, right?
Okay. So 50 compared to 30 would equal this divided by. So they're almost 5 times more likely.
Yeah,
And then you could just set that up for.
that is my relative risk, right? I think that is a term relative risk. It means like I'm 5 times more risky than middle-aged group. That is actually the relative risk. And compared with like the younger group, you just divide it by like 0.012 divided by that number, and you can see, okay, maybe I am 25 times more risky
Yeah.
to get this problem than people who is under 29 years old.
Okay. Yeah, I don't think he went over this type of relativity in class, so this is appreciative.
Yeah, I think this is one way to doing so to do this problem, and yeah, I am pretty flexible as long as you provide a rationale and you said okay, well, how you compare those data, compare those like 50 over 50 years old coal miners and the middle-aged one. Maybe you look at like I said, the difference of those two tables. You do some calculation. I mean, it works. It also works, but I think this way is the most easy way to answer the question.
Yeah, this absolute risk thing here, it makes sense to
Yeah,
it makes sense to me.
yeah.
Um, I think that's all the questions I have.
Okay.
I don't know if Olivia, Thomas, or Taylor, you guys want to jump in with something? I'm sorry, I've been hogging like most of the time.
Any other questions? Other people?
I need you to post these on YouTube.
Oh yeah, sure. I do that. I do that right now, actually.
Because James lost me a couple times, but I think I can probably find my way back.
Okay. Definitely. Okay, so if there's like no more questions, we'll just end by now, and I just post this on YouTube channel. It takes like about half an hour. I don't know why, but it has some checking process, I think, and yeah, it takes a little bit longer time.
Thank you for all your help, Victor.
Okay, sure.
I hope your test goes well that you just took.
I'll survive. I'll survive the test. It's a midterm, and it doesn't matter too much.
Okay, if you say so.
Sure.
I
See you
believe.
guys.
Yeah. Thank you so much.
Thanks, Victor.
See you. Have a good night.